The bomb that destroyed Hiroshima was 15 kilotons. It killed between 90,000 and 166,000 people by the end of 1945. It flattened 12 square kilometers of city. It is still, to this day, the reference point by which we measure nuclear destruction. The weapon in this simulation is 67 times more powerful. This is a 1 megaton hydrogen bomb, a thermonuclear weapon equivalent to 1 million tons of TNT. It was the standard warhead yield carried by Cold War missiles on both sides. Not exotic, not extreme. Standard. Everything you are about to hear is sourced from the US Department of Defense and Department of Energy's own reference document. The Effects of Nuclear Weapons by Glasstone and Dolan, peer-reviewed research from the National Academies of Sciences, and the MIT Press Reader's Analysis of Nuclear Weapons Effects. First, understand what makes a hydrogen bomb different from the atomic bomb dropped on Hiroshima. The Hiroshima bomb worked by splitting heavy atoms apart nuclear fission. The energy released was enormous by any conventional standard, but fission has a ceiling. There is a physical limit to how large a pure fission bomb can get before it destroys itself before fully detonating. A hydrogen bomb works differently. It uses the energy of a fission explosion to trigger a second reaction, nuclear fusion, in which light hydrogen isotopes are forced together under extreme heat and pressure to form helium, releasing vastly more energy. Thermonuclear bombs can be hundreds or even thousands of times more powerful than atomic bombs. The fission bomb at the core of a hydrogen weapon is not the weapon, it is the trigger. At Hiroshima, the trigger was the bomb. Here, the trigger is just the ignition switch. Detonation occurs at an airburst altitude above the city center, high enough that the fireball does not touch the ground, maximizing the blast radius and minimizing immediate local fallout. In the first millisecond, the weapon vaporizes itself. What was cold, solid material microseconds earlier becomes a gas hotter than the sun's core. This hot gas radiates energy as X-rays, which heat the surrounding air. A fireball of superheated air forms and grows rapidly. Within a millisecond, the diameter of the fireball from a 1 megaton airburst is 150 meters. Within 10 seconds, it has expanded to a maximum diameter of 2,200 meters, more than 2 kilometers across, and is rising at 100 meters per second. To put that in scale, the entire destruction zone of Hiroshima, the area of total devastation, fits inside the fireball of this weapon, with room to spare. During the period of peak energy output, a 1 megaton weapon produces temperatures of about 100 million degrees Celsius at its center, approximately 4 to 5 times the temperature at the center of the sun. Now the effects move outward. And this is where the scale becomes almost impossible to hold in your mind. The fireball itself extends nearly a kilometer in radius. Everything within it is gone, not destroyed, not burned, not collapsed, gone, converted to plasma. Beyond the fireball, heavy blast damage extends to a radius of 2.5 kilometers, where overpressure exceeds 20 pounds per square inch. Moderate blast damage enough to destroy wooden masonry structures reaches 5.4 kilometers. Third-degree burns from thermal radiation reach 11 kilometers. Light damage, including shattered windows, extends to 17 kilometers. Recall, at Hiroshima, severe damage extended to 2 miles. Total. That entire zone sits inside the moderate damage ring of this weapon. Even at more than 6 miles from a 1 megaton detonation, peak blast winds exceed 70 miles per hour. Those are hurricane-force winds. At 6 miles out, after the fireball has already risen into the atmosphere, now comes the thermal pulse, the flash of heat and light that travels at the speed of light, arriving before the blast wave. The thermal flash lasts many seconds and accounts for more than a third of the weapon's explosive energy. The intense heat can cause severe burns on exposed flesh as far as 20 miles from a large thermonuclear explosion. 20 miles. That is not a typo. Anyone in the open within that radius on a clear day looking in the direction of the detonation faces severe burns to exposed skin, not from standing near a fire. From the light alone, traveling at 300,000 kilometers per second, reaching them before they hear or feel anything. The early stages of a 1 megaton fireball are many times brighter than the sun, even at a distance of 50 miles. This is why nuclear weapons at megaton scale are categorically different from anything else in the history of warfare. The thermal radiation alone, before the blast wave arrives, before the fallout begins, reaches a scale that no conventional weapon, no matter how large, can approach. 16 seconds after detonation, the blast wave reaches a building 9.5 miles from ground zero. The shock wave arrives approximately 16 seconds after the detonation. Propagating across the building, the front wall caves in. Tiles are stripped from the roof. When the building is completely engulfed by the passing shock wave, the high pressure crushes the structure, and the high winds cause further damage as it collapses. That is not a building near the blast. That is a building nearly 10 miles away. Now the fires begin. And this is the part of a megaton-scale detonation that most analyses undercount. At Hiroshima, a 15-kiloton bomb individual fires merged into a mass fire within 20 minutes, consuming everything combustible within a radius of 2 kilometers. A mass fire initiated by a 1-megaton airburst over a typical urban area could involve areas considerably larger than 100 square miles, about 259 square kilometers, with peak fire intensities of perhaps 15 to 50 million megawatts. For reference, the entire city of Paris covers roughly 105 square kilometers. This fire zone is more than twice that area. Research has shown that fires simultaneously ignited by a megaton-scale explosion over an urban area would merge into a superfire of such scale and intensity with asphyxiating gases and gale-force winds that even those not fatally injured or trapped under collapsed buildings would have insufficient time to escape before the fire effects became lethal. The fire is not a consequence of the blast. It is a second weapon, triggered by the first, and it kills across a zone that extends far beyond where the blast itself caused physical destruction. Then there is the EMP, the electromagnetic pulse. The EMP threat from a surface burst extends as far as the distance at which peak overpressure from a 1-megaton blast equals 2 pounds per square inch, roughly 8 miles from ground zero. Within that radius, unshielded electronic systems, power grids, hospital equipment, communication networks, emergency response infrastructure are damaged or destroyed in the same instant the weapon detonates. The city loses its ability to coordinate its own survival at the exact moment it needs that ability most. Then comes fallout. Because this is an airburst, the fireball does not touch the ground. This significantly reduces the volume of soil sucked into the nuclear cloud and irradiated. Immediate local fallout is less severe than a ground burst of equivalent yield. But the fallout that does exist is carried downwind in an elongated zone that can stretch hundreds of kilometers depending on wind speed and direction. Radiation levels in this zone decay rapidly, but in the first hours after detonation, they are lethal to anyone in the open without shelter. The same advice from the 15-kiloton simulation applies here. But the zone is larger and the stakes are higher. Get inside a solid building, move to its interior, and stay there. Every hour of shelter in the first 24 hours after detonation dramatically reduces radiation exposure. So what does all of this add up to? At Hiroshima, with 15 kilotons, between 90,000 and 166,000 people died by the end of the year. 12 square kilometers of city were destroyed. A 1-megaton weapon would destroy approximately 80 square miles of urban area. That is not 67 times the Hiroshima damage, the number you might expect if you simply multiplied the yield. It is more, because at megaton scale, the intensity of thermal radiation effects drops off more slowly than blast effects as distance increases, meaning the range of fire and burn effects grows markedly faster than blast range as yield increases. The weapon is not just bigger than Hiroshima. It operates on a different physical logic. Hiroshima was primarily a blast event. A 1-megaton detonation is primarily a fire event, a superfire of a scale humanity has never experienced, preceded by a blast and followed by fallout. There is one final number worth sitting with. The explosive power of strategic missiles typically ranges from 100 kilotons to 1.5 megatons. The weapon in this simulation sits in the middle of that range. It is not the largest nuclear weapon ever built. It is not even close. It is the routine one, the standard-issue warhead that thousands of missiles carried, aimed at thousands of cities for decades. The Cold War did not end because the weapons went away. It ended because both sides decided, for now, not to use them. There are currently approximately 12,000 nuclear warheads in existence. Roughly 2,000 of them are on high alert, capable of being launched within minutes. This simulation is not history. It is a description of a standing possibility. Understanding it clearly is not pessimism. It is the minimum requirement for thinking seriously about the world we live in.